Hi, welcome to Podcast 6.2. Podcast 6.2 is all about bonds some more. 6.1, we talked about ionic, covalent, and metallic. So this one is not about the bonds inside of a molecule, but this one is about bonds between two molecules. So intermolecular forces. Let's get started. This diagram right here, this picture shows you a molecule. This is a polar molecule. It's got a positive and a negative. If you hear noise in the background, that's my family sneezing, the dishwasher going, it's raining outside, and the dogs are running around, just in case you wonder. But this is a polar molecule. It's got a positive and negative end. This is also a polar molecule. So this is one molecule. This is another molecule. So the bonds we're talking about are not inside of this molecule, but right here between the molecules. All right? So we call these dipole-dipole forces. So dipole-dipole forces are the forces between two molecules that have a dipole. One pole, two pole. One pole, two pole. Dipole. So this is a dipole molecule, two ends. This is also a dipole molecule, two ends. So the force between them is called a dipole-dipole. Now, you guys need to understand, dipole-dipole is a very general term. There are actually two kinds of dipole-dipole. There's a sustained dipole and an instantaneous dipole. And that's what we want to concentrate on, is the sustained one versus the instantaneous. During the summer of 2012, I went to a bunch of national parks, and I found this shirt, thought it was hilarious, and it's actually appropriate to what we're talking about. So here it is. This diagram right here shows you many dipole-dipole forces. Okay? Here's a water molecule and a sodium ion. That is a force between two molecules, a dipole-dipole force, and the negative end of the water is attracted to the positive end of the sodium. That's actually what sodium ions in water look like. They're kind of surrounded by water molecules. This is a methanol molecule, which is slightly polar, and a water molecule, and there's a slight attraction between those. That's a hydrogen bond. The bond between the hydrogen of one molecule and the oxygen of another molecule. So you get that brief attraction between them. Remember, we're not talking about inside of the molecule, we're talking about between two molecules. This is a dipole by dipole. This is not a hydrogen bond. This is one polar molecule attracted to another polar molecule. Just kind of a general sense. This is the one I want to show you down here. This is the one that people usually have the worst trouble with, the London dispersion or van der Waals forces. So let me take you back to the diagram that I showed y'all before. This diagram, if you remember that from 6.1, tells you that there are van der Waals forces or London dispersion forces and hydrogen bonds, and those are both types of dipole-dipole forces or intermolecular forces. I just wanted to bring y'all back to the thing that we have. Van der Waals forces or London dispersion forces, this is a non-polar molecule, and this is also a non-polar molecule. This is octane, and this one right here is hexane. There's no attraction between them. London dispersion forces are what happens when, for a brief moment, an instantaneous dipole, where for a brief moment it's a little bit positive and a little bit negative, a little bit positive and a little bit negative, and you get that case where there's a brief attraction from one molecule to another that's there for an instant and then it's gone. And this is how that happens. This is how London dispersion forces happen. That's a nucleus. That's a nucleus. The green cloud around it, that represents the electron cloud. Notice that the electron cloud is evenly distributed amongst them. That means it's a non-polar molecule. Nobody's more electronegative than anybody else. So you have one non-polar molecule, one non-polar molecule. Keep in mind that the electrons are always moving, and when that happens, we'll shift down to this next one. Here is an instance where, for a brief moment, the electrons, since they're always moving, travel over to one side of the molecule more so than the other. So for a brief instant, some of the electrons leave this side of the molecule and travel over to the other side of the molecule. Now notice, for a brief moment, this side has more electrons. This blue shading right here, that represents a slightly negative side. This red shading or orange shading over here represents a slightly positive charge. So this guy, for a brief moment, or gal, whichever way you want to go, this molecule for a brief moment is polar. This guy is still non-polar. If you've ever been on a boat out in the ocean or a bay or anything like that, anytime somebody sees a dolphin, everybody goes crazy. They're like, dolphin, dolphin! And what happens when everybody sees a dolphin? They always rush over to one side of the boat. So that's what's going on here. The electrons traveling around this non-polar molecule go, hey, look, a slightly positive sign over here. And they get all happy and excited, and they run over from the normal non-polar molecule. They all rush over to one side of the boat. So they rush over to here. And when they rush over to here, because they're attracted to the positive side on this molecule, you get this molecule. So looking at this state right here, you can see now you not only have one polar molecule, you have two polar molecules. The molecule on the left induced or made the molecule on the right polar. It attracted its electrons. Now y'all need to realize, how long does this last? A millionth of a second, for a brief period of time. That's all that this lasts. So it's an induced instantaneous dipole, or a London dispersion force. 99.999% of the time, they look like up here. But for that brief moment in time, they look like down here. That's what creates a slight bond, a slight attraction between these two molecules. What holds, or what kind of things have London dispersion forces? Everything has London dispersion forces. Anything with an electron has London dispersion forces. So non-polar stuff, polar stuff. What's most important, though, is usually the hydrogen bonding, because they're constant dipoles. The instantaneous dipoles tend to be very, very weak. The hydrogen bonds tend to be very strong, mainly because they're around all the time. But the London dispersion forces are responsible for stuff like air holding on to each other. So nitrogen molecules in the air sticking to each other. Argon, krypton, xenon, even though they're noble gases, they still will have an attraction to other gases just because of London dispersion forces. Some things, like geckos, have feet with little ridges on them, microscopic ridges, and those microscopic ridges actually attract through billions and billions and trillions and quadrillions and septillions and lots and lots and lots of London dispersion forces. That's what allows a gecko to walk up the side of a wall, is lots and lots of those London dispersion forces. Okay, but most of the time we're going to worry more so about hydrogen bonds and less about London dispersion forces. London dispersion forces typically only matter when it comes to non-polar things.
Run.